because that's the one where I was using the low definition camera. So like it doesn't matter. You can't read the whiteboard. This class has no textbook, so in lieu of that, we're trying out something new this semester where we record my lectures so that way people can actually see what I'm doing. And since I do most of my notes up here, it gets people going. So with the lab, we're going to do the big thing where I talk about testing in depth later, but I did want to talk about, I expanded the test case coverage from what I did the other day, and I just want to talk about some of the additions I made, because if I'm going to do this, I figured I should do it right. And so I did nearly the full suite of what you would do for production grade testing. There's one suite I didn't do here because for something that isn't production grade, it's a lot of work and it's very much overkill for the type of thing that we're working on. And I'll talk about what that is. So if we look at, for priority queue, I added some stuff to the interface too to make it consistent. So we have insert, delete, search, get smallest ID, extract smallest thing, size, array list, get array. And if we go over to test, there's a corresponding test for these. We have things like insert, and now we generate random students. Insert is actually, there's this big difference between here and the previous. Insert is now what I'm doing is every time I do an insert operation, I'm actually checking to make sure that that element is correctly inserted. So I can correctly insert at 0, at 1, at 2, at 3, at 4, at 5, at 6, at 7. Previously what I was doing is I was just inserting 10,000 elements and making sure they were all inserted at the end of the day, which is probably the case, but it's always better to check along the way to make sure nothing goes wrong between 0 and 1. You don't want to make any assumptions like that. This takes a little bit longer to code up, but at the same time you do get the guaranteed, okay, it works at 0, it works at 1, it works at 2, it works at 3, it works at 4, it works at 5. Now this adds to the running time of it, but all in all, the whole thing, the running time of all of the tests here is about 45 seconds. So it's not that bad. We have search test, and this one, I set up the array for search. I insert all the elements into the array, and then I go and search every element in the master to make sure that they're all in there. So I maintain a list of everything. I insert them into an array that I'm keeping track of all of my elements, and then I insert them into my data structure, and then I do a search that goes through all of them. I have a size test here because now I have a size one. This one is a little bit different because I want to test it in 4 different sets of sizes. And so what I do here is I randomly create sizes of different data structures. So I use 100 different sizes and I create them randomly somewhere between 0 and 10,000. Insert that number of elements and then verify that the size is actually the correct size. Does that make sense? Then for extract smallest ID, I always start off with my base case here, where I say try extracting something from a list that's empty. If the list is empty, what should it return? Nothing. So if it returns something, I get error. I expect I would never actually hit that error. What's more likely the case is that I would actually break and crash on extract smallest ID. It's very unlikely that that case would fail. It could, and I wouldn't check for that. It's much more likely that would fail and just crash. And that's really what this test is checking for. It's not so much the expressed fail condition, but really the implicit one of I run this and it crashes when I try and extract nothing. I also want to try and test explicitly for one element as well, because things tend to break at 0, 1, and 2. And so generally what you want to do when you're setting up test cases is pick your limits, test 1 beneath, 1 above, and then 2 inwards. Now upper bound these things is hard to do because how many students I'm going to have. If I'm testing this for Austin College, I would expect probably, let's say, 3,000 students at most. So we maintain the students that are here plus the last 4 years of students who graduated. So testing up till 10,000 seems pretty safe. That's giving it substantial load coverage. In addition to expressly testing 0 and 1, what I do after that is I now so I have a test for 0 elements, I have a test for 1 element, I also do a test for 2 elements just to make sure nothing goes wonky there. After that, I then build up an array of 10,000 elements and then burn it down to the ground. I try and extract every element and make sure every extract works as well. Git min test. Similar thing here, except now I'm not extracting elements. So I have to make sure that it is still correctly getting all of the minimum elements in here, but I'm not removing them. So sort of the load for it is a little bit different. Delete. Similar, what I do as well in this one is now I do another burn to the ground where I randomly choose an element in my array, delete it, and then I delete it both from the master and from the new one, from the master and the linked list, and then I randomly delete, and I choose another one in my updated master list, and then randomly delete that from both of them, and make sure the element that's being deleted actually matches the element that I say should be deleted, and that the entire linked list deletes at the end. And I'm checking the size as it's going down each time. And that's the end of the list that the things that I've built up here. One thing that's important to note is that you'll note that some of these things, like for example, search requires insert to work. And so it's fine to have these things that build up off of each other. You just need to make sure that you're balancing them. You can't have basically all the tests, that multiple tests can pass because there's a mistake in one. So you kind of need to make an express test for each of the methods in your interface. And with that express test, you can then say like, okay, we assume that if this test is passing, insert is working. And so that means we can then use insert and other methods. And so insert and search are sort of the base ones here. And from there we can circle the size and other things and making sure they're working too. The one test case I did not include in here was I didn't include a test case where I randomly insert, delete, extract, and where I randomly apply all of the different interface options from my interface. That's usually a staple of real test case coverage when you're talking about production grade work, because you want to make sure, this is all very contrived scenarios. This is very specific. These are stress testing scenarios, and we are testing the load, we're testing the performance, we're actually not doing express performance testing here. But you're kind of saying, okay, yeah, this is taking a long time. If one of these tests was taking 10 minutes, you'd probably have a pretty good idea that something's gone wrong. We're not doing an express performance test here, but we get a pretty good idea of how they perform. But we are testing a load test, we're testing the edge cases, but you also want to test and make sure that things don't go wrong as users randomly do shit on their systems. And so you want to, if I were doing this in a production grade in addition to this, what I would have is I would write a script that would randomly create a series of inserts, extracts, deletes, what have you, and then run through that and make sure the list was maintaining itself with each of those commands. Doing that is a lot of work. And that level of diligence is not something I would really expect unless you were doing something that's production grade. So you're talking about stuff for software engineering class, for those who are in there. That's the type of testing I would expect in sort of the final testing of production grade software. If you're going to use this in a real product, I would expect that type of behavior. For a class project, this level of test coverage is sufficient.
Sorry, for the checking to see if the list is the same when you randomly generate the list, how do you keep track of the...
You use a data structure that you're aware of. And
so
so, right, so here I use an array list to keep track of it. I can do all these operations on an array list, but I would expect they'd be slower there. And so you're basically using the slower system, and then once you have this set up, you could then use linked list as your base to test the other data structures as well.
So with the hash table, do you have to do like a linear proving method and then compare that to an array list?
With the hash table, you're only going to have to be doing the linked list approach. So we have the array and then a linked list that follows it. So what you would want to do is you would want to make sure that things are. You wouldn't have to test these type of data structures. It's not as important that it's storing in you need to make sure that the interfaces are what's working.
But they're just named.
Yeah.
So would a size test work with a hash table?
No, it would not. And so if you look at the hash table, I added a hash table interface up here, and it has insert, delete, and search.
Well, yeah, but I'm talking about in testing phase.
Yeah, no, well, there's not a method for it, so you wouldn't have to test it. This is what you have to test.
Well, I'm talking about, I know that, but I'm saying like insert. So
Uh-huh.
whenever you're testing insert.
You'd have to test it you'd have to use search with it too.
Okay.
Yeah. Yeah. So yeah, you can't test that.
I'm trying to see if you're testing insert and you're just testing size, then you don't know if it's inserting in the correct location. So how do you test to make sure that it's in the correct location if you don't have another aware data structure?
The other way, there are two approaches you can do for checking that. One is that you can manually troll through your entire thing and make sure that you know where it's being inserted, or that you have basically how it should. You have a verification of it should be in this element in the inserts data structure, and you actually build helper methods into the hash table that aren't exposed here. And so you would have public methods that exist solely for testing.
Like the
Basically,
testing methods.
yeah, private that would not they'd all be public testing methods. But so public testing methods here are helper things to these are things to generate random data. So that's different than, for example, really I have one helper here, and that's get array. You would never actually get array of a data structure. That defeats the whole point of it. But this is a very useful tool, and I added it to the interface simply because it's going to be so useful for your testing that I wanted to make sure that you actually have it for all of them. If I were making this as production code, I would not have get arrays to the interface because that's not what you would want to have. But so what I would do if I were trying to test specifically hash table, I would have a get array method for like get array or get linked list for particular items that basically exposes this to the end user with the knowledge that, yeah, at the end of the day, you'll make this private. You come back here and make this private or protected. You can cheat by making it protected and then making it testing subcase. Don't do that. That's way too complicated.
And then with that, you can just access the array and check to see. And I guess you would test the hashing protocol.
Yeah, you'd want to test if you were being really explicit about making sure all the intermediate functions work. There's different levels of testing you can do. There's an interface testing approach where you just test the interfaces. In a lot of code, that's sufficient because when you test just the interfaces, you're testing how it exposes it to the outside world. For these type of data structures, that combined with performance testing would be enough. Now, if you're doing something where other people can access intermediate parts of it, then you would want to also test every private method you have here and make sure the internal data structure is behaving exactly like you want it to. And so in that case, you would want to do things like testing, have testing methods that would touch things that the end user never would touch.
Okay. So then with the hash, for instance, like provided that you test a hashing protocol
Mhm.
and you put every randomly generated student into an array list, would you just do a .contains check in the hash table?
It wouldn't be in the array list, it'd be in a linked list. Because remember the hash table.
What I'm saying is that if I have an array list of all the random students,
Yes.
and then I have my hash table, if I iterate through
Yes, that's exactly
all
what you
array
do.
and all linked
Yep.
lists.
Yeah, that's if you look through the list here, that's what I do. That's basically what I do for search. Is I can build up the master list, array list, and then I basically say for each element in there, check and make sure, do a search on it.
That's there somewhere.
And so that's the way I would test it. Is I would do, I would actually have an insert and probably search test combined because of that. I think that with the hash table, because the way it's stored, there's no secondary check. You are going to have to do an insert and a search test together.
Okay.
So, and that's fine. That happens. If you want to go the extra mile and actually test things explicitly, you can do that.
And then just comment from my
Yeah. But does that make sense about sort of this approach to testing?
So, is it better to use fails inside the statements rather than like assert saying or assert equals?
I don't know. I like fails more. I don't know if there's. Higgs does more industrial Java code. My industrial strength code has typically been Objective-C and C. I don't know from a Java perspective which one would be better. I would ask Higgs which one he prefers. So I like these if statements more.
Is this a test you made within a class, or is this like J-unit testing?
J-unit testing.
Okay.
And so we'll do a session. I think I'll try and set up something for CS lunch this Friday for those who can make it to actually go through J-unit testing.
Would it be possible to put something like this up on like Moodle?
This is on Moodle.
It is? Okay,
Yeah,
awesome.
this is exactly on Moodle. This entire
I was gonna ask you that, yes.
this is on Moodle. So, and I updated it this weekend. So if you downloaded it on Friday or very early Saturday morning, get it again. So I don't think you looked at it before.
Yeah.
Yeah. So, but yeah, look through it. And honestly, for the priority queues, I haven't given you testing for hash tables here, but for priority queues, you can basically just rework this testing class because it took longer to write up the test cases than it took to actually write up the rest of the system. Far, far longer. Now for 2-3 trees, I don't expect that would be the case, but you basically have the testing methods here. All you would need to do is rework these for 2-3 trees and binary trees. They shouldn't. I honestly think it should not be much more than just changing linked list node to binary tree node. I don't think there's actually much more that you'd have to do than just doing some minor changes like that. Any questions about that before I go on with the lecture for today? Alright, so where are you, Keynote? So, any questions about 2-3 trees before we go on to delete? So let's give. There's one last thing I want to do before I go into delete. Let's talk about the schedule. So the way the schedule up until spring break. So I am going to. We're going to be doing data structures and algorithms this week and all of next week, and so we're going to have the test of our data structures and algorithms the day before spring break. Friday before spring break.
I mean, we could rather have it the day we get back.
Yes. And that means you were the one person who screwed in both of my classes. Sorry.
So there'll be no lab over spring break, right?
What? No, because what's going to happen is I'm going to abandon you after spring break. So at that point, what's going to happen is Michael Higgs is going to teach AI segment of here, and so he'll teach AI for 4 weeks. Whereas I go over to software engineering and teach software engineering for 4 weeks. At which point we're going to switch back for the last 4 weeks of the semester, where I'll teach theory of computation and he'll teach software engineering to finish off.
That's so much. How many weeks do we have for spring break?
8.
Only 8?
Only 8?
Oh my god.
It's actually spring break comes earlier this year. So normally spring break comes 6 or 7 weeks, but this year we decided to permanent align with Sherman ISD, and so from now on we will always have Sherman ISD spring break, and
Why does that matter?
because some professors have kids who live in Sherman and they would like to be able to go on spring break. I'm the only professor who lives in Allen, so
So let's use Allen's.
Jay Lee too.
Jay Lee lives in McKinney.
A lot of people live in
Yeah, a lot of people live in McKinney. I live further south than anyone.
Sherman ISD is the wisdom schools, aren't they?
With this one?
The Sherman ISD usually has spring break on the same time as those schools.
Sometimes,
So we-
not this year,
Yeah, why
but
don't they just get with this school?
Why don't we just burn it?
because honestly, Sherman ISD is bigger than this school.
I don't even think most of Sherman knows there's an Monster College.
We're on the water tower. So, and the side, did you come in? But anyways, but yeah, so we'll be doing the test the day before spring break. We'll have spring break, and you'll come back, and Michael Higgs will be teaching for AI.
Will the switch affect your office hours?
The switch will affect them in the sense that it'll be 9 to 10, as opposed to it'll only affect the office hours in that sense.
Do you have office hours at a different time other than right after this class?
Yeah, I have two. I have.
12:30.
I also have from 12:30 to 2, and then 11 to 1 on Tuesday, Thursdays. So, if you can't make any of those times, you can let me know and we can try and work something else out. So let's talk about delete. So the way that delete works is when we delete a node, we now have introduced the possibility that we might have we might be setting ourselves up for catastrophe. And so we're going to be deleting a value in here. And so we have two cases. We could end up deleting a value in a leaf node, or we could delete a value in an internal node. What's going to happen is that when we delete an internal node, what we will do is we will try and swap the internal node with a leaf node. So remember we had this thing with binary trees. Oh, and by the way, if you downloaded the binary tree notes, get them again recently because I fixed the spelling mistake in there. As remember, the spelling mistake was when I called something get biggest when it was actually get smallest.
On the slide.
On the slides, yeah. Where we have an element 10 here, and then the next smallest element, if we had 5, 8, 9, would be stored at the leftmost element. We have a similar property here, where we can, if we have an element in a 2-3 tree, if we want to find the next biggest element, we just take the leftmost leaf node on the right-hand side. And so if we want to delete an internal node, what we do is we first just swap those two out. The rest of the tree structure is fine, and then after we swap them out, we then delete a leaf node. We don't, not node, leaf value. I shouldn't mix nodes and values here because a node can contain two values. We're not deleting a node, we're deleting a single value. Does that make sense? So let's talk about deleting a leaf value. Deleting a leaf value from a 3 node is super, super easy. You just get rid of it. So let's build up a 2-3 tree and start working through some examples as we do this. So, what number should I start off at my top?
7.
7 and
15.
50. Now that's going to be really small. Let's do 420 so that we have room to spare. So, you're wondering what it was going to come up in here.
And Tim said it like literally like half a second before you said
It could have been 1138. You didn't know that. But I wanted to give myself room to grow. So that's why we have 1138 here. I use the same set of numbers in all of my classes, which are chosen for random reasons. Who knows? Okay, so, and then we'll make this one, let's make this a 3 node. So we have 1138, let's do 512, woo, powers of 2. Then here we'll do 490, let's make this one a 3 node, let's make this 640 and 1137, and then 2001 Space Odyssey. Yeah. That one? Yes. I can read it fine. Alright, then let's make this one, I heard 15 shouted earlier. We'll make this one 419. We'll make this one 8. We'll make this one 3.14. We'll make this one 5, and this one negative 15 billion.
So are all those leaf values supposed to be on the same level and there's just some drawing issues?
Yes. Yeah. They just got crowded out. So, so what happens if we want to delete, if we wanted to delete 1138? Well, no, 1138 is not. It's not a leaf node. It's an internal node.
Switch with 2001.
So we could either switch with 2001 or 1137. We could swap with the next smallest or the next biggest. Either one of those works. Let's switch it with 1137 because that will make our life a lot easier. So we'll swap those two. And then we have 1137, 1138.
Should we always choose the same one, like be consistent?
You should be consistent in your program of smallest and largest. So I'm doing it in this one because you can when you write the program to begin with, you choose one approach. It actually doesn't matter if you're consistent, but you should choose one approach because it'll be easier to program. It is easier for demonstration purposes because we have a 3-node here. So that's what I wanted to illustrate with this. So that's why I chose this way because it's easier. But
Would that not create errors in your program if everywhere else in your program, the middle number is a smaller one, and then when you're swapping it to delete it, suddenly the middle number?
well, because you're either swapping it with it needs to be larger than everything to the left of it. It will cause problems in a second if we didn't delete 1138. But it needs to be larger than everything to the left of it and smaller than everything to the right of it. Because we're going to delete it in a second, it's not going to matter at the end of the day. Because it's a momentarily incorrect. There is this incorrect thing of 1137 is there, 1138 is there. But that won't matter because we're going to delete 1138 from here. But the rest of the tree is fine. Does that make sense?
Yeah.
So everything else in the tree is fine. Now we need to delete 1138 from the tree. So how do we do that? Well, it's a 3-node. So what's the easiest way to do that? Just get rid of it. And we now make 640 just a 2-node. So that's the simplest approach.
So once it's a leaf node,
Once it's a 3-leaf node. They're called 3, by the way, they're called 3-leaf nodes because they could have 3 children, even though they only have 2 values in there. So if you're like, why is it called a 3-node, even though there's 2 things in there? It's because 3 nodes can't have 3 children. 3 nodes can't have 3 children. It just happens this one doesn't have any children, but it could. So don't worry about it.
Has to do with starting at 0.
Yeah, it's start with not this case actually. This one doesn't. This is not that obscure. Okay.
in this example, I mean 1137 is like pretty much the same as 1138.
Mhm.
But if there was a big difference,
It doesn't matter as long as because this node, if we get the largest smaller value, that largest smaller value is going to be larger than everything else in this subtree. And similarly that this largest smaller value, the smallest larger value, is going to be smaller than everything in this tree. So it basically makes these 2 trees perfectly fine. So for example, if we were to delete 7, we could replace 7 with the smallest larger value or the largest smaller value. So we could replace it with 5 or 8. And if it was replaced with 8, notice that everything, like there's glue up we'd have to do here because we're deleting a 2-node, and that'll cause problems that we'll get to in a minute. But 15, 419 are both bigger than it. Similarly, if we were to delete 420, replacing that with 419 or 490 doesn't upset anything else in the tree aside from that one imbalance. Everyone cool with that? Alright, so deleting a 2-node can cause underflow. So when we delete a 2-node, we can get a parent that has 2 values may only have 2 children, and a parent that has 1 value may have only 1 child. So how do we deal with those? We deal with them the way that sounds most awesome, with fusion. What we need to do if we have fusion is we can start transforming nodes into other nodes. And so we can borrow from neighboring nodes that are present. So let's go through this example. So suppose we have the system where we have, let me write this up over here so you can see specifically. Unfortunately, it's not in this one. We just deleted the node that would have helped us. 4, 9, 2, 6, 8, and then I'll say 10. So let's delete 10 from here. What's the problem now?
There's still a node there.
This is a 3 node, and if everything that has 2 values in it should have 3 children. It has 3 children or none, and it has 2. So how do we fix this?
You make the 9 the right node and make the 8
Right.
the
So what we do here is we say, okay, these are all leaf nodes, remember, that we're deleting. So we say, you know what? 8, you no longer get to be a 3-1. You're going to replace one of your 2 parent values. Again, getting very disturbing. And then make one of your parents now your child. What?
Science.
Yeah, science. Yeah, so you take the 9 value, bring that down, and take the 8 value and bring this up. And so again, there could be substantial differences between these, but because of the way these things are structured, there's nothing on the right-hand side because you're in an underflow situation. So you can put whatever you want to in there. That value needs to be, this value is larger than either the right-hand side of this one, or if you were deleting 2, it'd be smaller than that value. And so you can bring that down and put that up and still maintain the tree structure.
So if it was just a 2 node with 2 children, would you just delete one which got children and move that up?
We'll get to the 2 node one in a second. So we have a bad case where we have no 3 node adjacent. And so if we have no 3 node adjacent, what we'll need to do is we'll need to turn the parent 3 node into a 2 node, and then make its 2 children either 2 nodes or 3 nodes, depending on the case. Just remember, you don't actually have to program up delete for your lab. Just going to remind you about that. I did that my first year here, and I still hear people complaining about it.
I wonder why.
Does anybody actually use this?
Oh yeah, this is widely used.
Really?
Oh yeah, because it kicks ass. Just because it takes the developer a long time to make doesn't mean it's not awesome.
It isn't built in.
What?
You don't just have 2, 3 trees built in.
Yeah, it's not. It's not. What happens is people will make these data structures for. They'll usually make their own custom version of it,
And they just reuse it.
and they just reuse it for their project. 2, 3 trees themselves are used occasionally, but there's a far more complicated version of this called B trees, where instead of just having 2 nodes and 3 nodes, you have basically an unbounded number of elements in it. If you take databases, Higgs will talk about them a lot. That process is far more complicated, but that's how databases store data. And so 2, 3 trees are a special case of databases. This is far simpler than what you actually see widely used. So.
Why would you want to use a 2-3 tree as opposed to just a good old binary search?
You'll see when you do your lab and you do a performance test, especially when you insert them in order, the performance of the 2-3 tree will always be log n time, whereas the performance of a binary tree in the worst case is linear time. And so you look at you imagine Facebook database, like how many Facebook posts are there a second, and they need to be able to pull out the most recent ones. If that was running linear time and you're talking billions of posts a second, ouch. So that's why. Now, generally, if you need things in sorted order, you're using either a 2-3 tree, an AVL tree. A red-black tree is probably what's most commonly used, and we talk about that in DSA. We choose a 2-3 tree in this class because it's a leader for both B trees and databases and for red-black trees in upper level. So you can go either way with this one. But every binary tree has its own, every balanced tree has its own advantages and disadvantages. My personal favorite is mergeable trees, where you can take them, you can blend them together like that. But those aren't for this class. So let's go through this example where we have 9, 14, 5, 7, 10, 420. And then let's delete 420. 420 is gone. We don't have a neighboring node we can borrow from. So what we have to do here is we have to take this 14 and bring it down. And so we take the 14, put it down here into the 10, and this is why it's called fusion, because you're fusing those two together. And now we've made it a 5-7 and a 10-14. Notice that, so let's do 9, 14, just a single 5, 10, 420. You delete the 420, you have the same bring 14 down behavior. Now it's just 9, 5, 10, 14. What I wanted to hit home with this example is that if you're not next to a 3 node, it really doesn't matter what your other sibling is. It can be whatever you want it to be. It doesn't really have any impact on it. Any questions about that? So let's see what happens when you delete a 2 node. So we'll delete 14. This causes a pretty bad underflow. So what we have to do is we have to merge 5 and 17 under what's called an empty node. The empty node is, again, an illegal state that you can't exist in for a long period of time, but it's there to maintain balance. So we have 517 singularly under this empty node. Now what we have is, it's as though this was the node that was deleted. So now we need to fix up that situation. Perhaps the empty node was part of a 3, perhaps an empty value was, could be, there's a 3 value over here and we could merge them and solve them that way. If not, we then have a similar empty flow up top and we fix that as well. Eventually what will happen is that underflow will bubble up all the way to the top. It'll either hit a place where it has a sibling that's a 3 node, or it'll come up to the top and you'll lose a level on the tree. And so now we end up having a smaller tree. Oh, there's the delete. Not so bad. Except for that one thing. Fix underflow. Bam. It's not so bad.
Your root is officially like dead now? Or?
No, the root's not dead. It's as though it bubbled up to the top. And so you would change you'd say, it sort of pops off the top.
So why couldn't you delete it on top and not the bottom?
Because you basically say, oh, this is what's happened here is it's not so much you've lost a level here, because there's always one root node, and so it's basically the root is an exception to all of the other rules in there because there's one thing pointing to it. So once the root becomes null, it just replaces. It's not as the root ever becomes null, but it's basically it says, oh, let's just skip past that. And so you notice that in this tree, there's 3 levels. Before we delete the node, there are 3 levels.
So if that happens enough, does it?
It'll kill the tree. Yeah. And so
It will slow down the tree every time you do that.
it doesn't slow down the tree; it makes it smaller. So it actually makes the tree faster. But it removes the elements from the tree. So this tree now has 2 levels in it. Right?
So that tree's fast.
Yeah. So let's start killing off this tree. That sound good? Okay. So Let's delete 640. 640 has neither neighbor that's a 3 tree, right? So what we have to do here is, I'll step back to the step so you can see it, the bad case. So 640 has neither one that's here. Now because of the middle node, we have an option of which one we want to bring down. We can choose either one of those. For reasons that I have no idea why I'm choosing, I'm going to bring 512 down and make it 490 and 512. There's no reason I could have chosen 1137 and 2001, but that's just the decision I've made. So now we have 1137, 490, 512, 2001. Everyone cool with that?
So you're allowed to have a 3 node as a child of a 2 node?
That's perfectly fine. Now let's kill 2001. What happens? Yeah, we can take 1137 and make it a node like that. Okay, now let's kill 1137. So killing 1137 puts us in this situation. So now 1137 is gone. Now I'm going to draw that with a dead node for now. Now we need to fix up these nodes. So what we do is we take 490 and 512 and we change the structure of this tree so that we maintain balance. And so now we put our dead node there, 490, 512. We now need to fix that node up. Well, how do we fix that node up?
Aren't those supposed to be a 3 node?
Oh, sorry, yeah. So now how do we fix this node up? Well, now we have a 3 node above us, so we can start using the swapping approach that we had before.
That 3 node with no children was still valid, or does the 3 node have to have 3 children, or is
Yes.
it 3 children or no children?
3 children or no children, there's no intermediate.
Yeah, because that's right there. You've got a 3 node with no children. You could easily couldn't you just?
That one's not the problem. It's this mysterious floating red dot in our tree that's the problem. That's basically a deleted node in our tree that needs to be fixed up. And so we have to find a way to fix up that node. So what we need to do now is we will bring 420 down. That's madness. So if we had a 3 node over here, it'd be easy because we could just we could do that borrow and swap. So we know we don't have a 3 node here because we can't do that borrow swap. So that means it's a 2 node. So because it's a 2 node, that means we can take 420 and bring it down there. Now we can take that child and glue it up like that. Woohoo! This tree still isn't dead yet. I want this tree to lose a level. Okay, so let's delete 490. How do we do that? Just delete it. I like how the deletion process is like easy, easy, easy. Oh god. Okay. So we did 490. It's now a 2 node. Done. Let's delete 512. We delete 512. It doesn't have a 3 sibling we can borrow from. So now we need to bring down the 420. And so now we have 419 and 420. Now we'll delete 420. No, let's keep 420 around. We'll delete 419. That one's easy. Now we'll delete 420. Now we have our dead node right there. So what do we have to do? Well, we have to do our underflow fix-up with the parent node. So now we take 8, 15, dead node. We don't have a 3 node next to us. Otherwise we could just do the swap thing. We know that must be a 2 node, so what do? We bring that down. And so we make that 3, 14, and 7. Make that there. Bubble up that to the top. Now our dead node's at the top, so it's like cutting dead hair off. You're like, goodbye, hair. The tree has just gotten a haircut.
Sure. Well, wait. You probably bleed hair from haircut. It's that's just bad.
Yeah. Hair's already dead.
Is it all hair dead?
Yeah. What? All hair is dead, yeah. At least to me. No, that'd be sad if your hair was infected with zombieism. Like your hair was a zombie, but the rest of you wasn't. What'd you say, Gabe?
I was gonna say, can I call it bleeding haircut?
In your private methods, yes, but not in your public interface. So you should that would make your delete even easier, because then your delete would be delete value call haircut. There, look how easy delete is.
Let's just fix underflow.
Yeah, just fix underflow. And so after all of that, we've managed to make our tree 1 level shorter. And that's the process by which we 2-3 things up. Are you gonna have to do this entire thing on the test? That seems like a good idea. 50-minute test.
It's okay. You can have that one question.
Wait, so does that mean you have to write a bunch of pseudocode for our answers?
Oh no. No, you have to walk through algorithms. What you will be expected to do on a test for this is I will give you like this and say delete I won't give you this. I'd be like delete 14. Show me how that works. So I'd give you a very simple example and be like delete this value. Show me the steps you do for doing that. So nothing terrible, but I'll give you guys some homework assignments over it and you'll see the type of questions that I'll ask. And then I'll ask one really pain in the ass question. Want to make you build up a tree and then tear it all down because I feel like wasting your time. No,
We only have 15 minutes.
not for a homework assignment.
Oh.
But yeah, cool. So that's it for today. And I will go post all of these online.